Last part of the video, we're going to talk about Riemann's sums, which are given by this formula. Okay, so given a function f that is bounded in this interval, right, AB, as we have seen so far, then we can write for any partition P, we can write this sum, right? This is the value of f at Ci, where Ci is any point between the extrema of the interval, right, times xi minus xi minus 1, right? So whenever you choose a value c, you are going to give a Riemann sum. Okay, for this definition, it's clear that there's this condition: any Riemann sum is going to be smaller than the upper sum, and it's going to be greater than the lower sum. Okay, for corresponding to that partition. Okay, so if f is integrable, right, so then we have that, let's see, if f is integrable, then we have seen that the limit when n goes to infinity of the difference between ufpn minus lfpn with a sequence of partitions that get finer and finer and finer is going to be 0, right? But now, using the sandwich theorem, right, this implies that the limit of, so that means that this difference is 0 and that both partitions go to the integral, right? So that using the sandwich theorem implies that the limit when, if you choose any sequence of partitions that gets finer and finer so that this thing goes to 0, the limit of s with respect to that partition is going to be the integral. Okay, and that thing is going to be useful for calculating some limits. So for instance, suppose we have the limit when n goes to infinity of the sum from k equals 1 to the n of 1 over n plus k. Right, so this is not a series because the sum is defined in terms of n. The general term also depends on n, right? But we can rewrite this as this. This is the limit when n goes to infinity of the sum from k equals 1 to n of 1 over n, and then we have 1 over 1 plus k over n, right? So now 1 over n can go outside, or if you want, let's see, wait a minute. So this 1 over n is, you can think of the width of the interval, right? Of the interval of the partition. The intervals in the partition, right? And this is f at the interval k over n, right? So this is the function f is 1 over 1 plus x, right? So this is exactly this. This is f at some point in the interval, right? This is the difference between the interval. This is the sum, right? And we know that the limit of this is going to be the integral of this function between a and b, right? Now, in this case, a, if you see here, when k equals 1, this is from 0 to 1. Okay, the integral is from 0 to 1. Okay, and so we just need to compute that integral. Okay, the primitive of this, the integral of this, we'll see later on how to compute this, but this has to do with the primitive of this. Okay, another example. We have the limit when n goes to infinity of the product of k equals 1 to the n of 1 plus k over n to the 1 over n. Okay, in order to get this, we call this is L, we compute the logarithm of L, and so this is the logarithm of all of this, which is the limit when n goes to infinity of the logarithm of this. So you have 1 over n, the logarithm of the product, which is equal to the sum from k equals 1 to n of the logarithm of 1 plus k over n. And just like before, 1 over n is this thing, and this is this value, right? The value of the function f, which in this case is the logarithm of 1 plus x at the right end of the interval, right? So the limit of this is going to be the integral between 0 and 1 of the logarithm of 1 plus x. Okay, dx. Right?